Welcome to Chapter 9 in Precalculus. And this is where our study of precalculus actually starts to overlap with calculus. So Chapter 9 is going to be very important. Let's start off the first section, 9.1, Sequences and Series. Now the definition of a sequence is going to become very important. When I use the word sequence, I simply mean a list of items. The domain will be the list of positive integers. And if we looked at it in traditional function notation, f of 1 would be the first element. We would call this a sub 1. F of 2 would equal the second element. We would call that a sub 2, and so on and so on and so forth. When you see three dots, that's called an ellipsis. And an ellipsis simply means that the pattern continues. So after a sub 4 comes a sub 5, then a sub 6, and so on and so on and so on, until we get to f of n, which is a sub n, and then another ellipsis, so that means the process keeps going. So here's the definition of a sequence. Put this in your notebook, please. You're going to be held accountable for a Chapter 9 notebook. An infinite sequence is a function whose domain is the set of positive integers. The values are a sub 1, so there's a first element. There's always a first element. A sub 2, a sub 3, a sub 4, and then an ellipsis going up to a sub n, and then an ellipsis indicating the process continues. These are called the terms of the sequence. If the domain of the function consists of the first n terms, which is the first n positive integers only, and if it comes to a sudden stop, that's called a finite sequence. Example 1. Write the first four terms of the sequences given by the following. A sub n is defined to be the expression 3n minus 2. All right, here we go. A sub 1 would equal 3 times 1 minus 2, and that's 1. A sub 2 is 3 times 2 minus 2, and that's 4. A sub 3 is 3 times 3 minus 2, and that's 7. A sub 4 is 3 times 4 minus 2, and that's 10. So the first four terms are 1, 4, 7, and 10. Part B, a sub n is defined to be the expression 3 plus negative 1 to the n. So a sub 1 is 3 plus negative 1 to the 1, which is 3 minus 1, which is 2. A sub 2 is 3 plus negative 1 squared, which is 3 plus 1, which is 4. A sub 3 is 3 plus negative 1 cubed, which equals 3 minus 1, which is 2. A sub 4 equals 3 plus negative 1 to the fourth, which is 3 plus 1, which is 4. And the sequence is going to do this forever, by the way. It's going to bounce back and forth between 2 and 4. 2, 4, 2, 4, 2, 4, 2, 4. Whenever that happens, the sequence is said to be oscillating between two values. Let's talk about alternating sequences. Write the first 5 terms of the sequence given by a sub n is the expression negative 1 to the n, all divided by 2n plus 1. So let's write out the first 5 terms. A sub 1 is negative 1 to the 1 over 2 times 1 plus 1. Well, this becomes negative 1 over 2 plus 1, and that's 1/3. Negative 1/3. A sub 2 is negative 1 squared over 2 times 2 plus 1, which is 1 over 4 plus 1, which is 1/5. Positive 1/5. Negative 1 to the third power over 2 times 3 plus 1 is a sub 3. That's negative 1 over 6 plus 1, which is negative 1/7. A sub 4 is negative 1 to the fourth power over 2 times 4 plus 1, which is 1 over 8 plus 1, which is positive 1/9. A sub 5 is negative 1 to the fifth power over 2 times 5 plus 1, which equals negative 1 over 10 plus 1, which is negative 1/11. So this sequence is alternating because it switches in sign each time you move to the next element. And what I like to do is whenever you have a negative 1 to the n power, I like to call that little piece the alternator. So it's that negative 1 to the n power. Every time n is odd, you get a negative result, and every time n is even, you get a positive result. I like to call that the alternating piece. Simply listing the first few terms is not sufficient to actually define a unique sequence, however. The nth term must be given. To see this, consider the following sequence, both of which have the same first three terms. 1/2, 1/4, 1/8, 1/16, all the way up to 1/2 to the n. 1/2, 1/4, 1/8, and then all of a sudden 1/15, which leads to a completely different expression. So this expression that I'm circling here with my hand is the nth term. This expression that I'm circling here with my hand is the nth term. Example number 3. Write an expression for the apparent nth term a sub n of each sequence. We have to use the word apparent because we're going to make our best guess as to what it is. Well, I see the sequence 1, 3, 5, and 7. So the domain is the integers 1, 2, 3, 4, and so on up to n, and these are like the y values 1, 3, 5, 7 up to a sub n. Well, there's a pattern here emerging, and each time you increase up to the next number, each term is one less than twice the number. So for example, 2 times 1 minus 1 is 1. 2 times 2 is 4 minus 1 is 3. 2 times 3 is 6 minus 1 is 5. 2 times 4 is 8 minus 1 is 7. So it seems that the apparent pattern would say that a sub n, that's the nth term, is equal to 2n minus 1. Part B, notice the sequence is alternating, which means we're going to need an alternator, -1 to the n, or sometimes even -1 to the n plus 1 power. All right, so how is this going to work? Well, first we list out the domain, 1, 2, 3, 4, so on and so forth, and then the actual terms. So the question is this: how do I go from 1 to 2, 2 to -5, 3 to 10, 4 to -17? Well, let's look at it this way. Probably the 3 to the 10 and the 4 to the 17 are the most obvious. We know that 3 squared is 9 and 10 is 1 more than 9. And we know that 4 squared is 16 and 1 more than 16 is 17. So it looks to me like there should be an n squared plus 1 somewhere in the nth term. But it also alternates, and the first term is positive, which means that we're going to have a -1 to the n plus 1 power. So if I start off n at 1, 1 plus 1 is 2, and so -1 squared is a positive 1. And then 1 squared is 1, 1 plus 1 is 2, and so I get positive 2 for the first term. Let's go to the second term. Put in a 2 here. 2 plus 1 is 3. -1 to the third power is -1, so that's a negative number. 2 squared is 4, and 4 plus 1 is 5, so I get -5. So it's working. The sequence is working. Some sequences are defined recursively. To define a sequence recursively, you need to be given one or more of the first few terms. All other terms of the sequence are then defined using previous terms. A well-known recursive sequence is the Fibonacci sequence. So, the Fibonacci sequence is defined recursively as follows. A sub 0 is 1. A sub 1 is 1. Every later value, we're going to call it a sub k, is equal to a sub k minus 2, that's 2 predecessors, plus its immediate predecessor, a sub k minus 1. This will always be true when k is greater than or equal to 2. So let's look at how this actually works. Define a sub 0 to be 1 and a sub 1 to be 1. Then a sub 2 is equal to, following the pattern up here, a sub 2 minus 2 plus a sub 2 minus 1. But that's equal to a sub 0 plus a sub 1, which we already defined as 1 and 1. So 1 plus 1 is 2, and that means the second term is 2. A sub 3 is a sub 3 minus 2 plus a sub 3 minus 1, and that becomes a sub 1 plus a sub 2. Well, we have a sub 1 and a sub 2, it's 1 plus 2, which is 3. So a sub 3 is 3. Now here's where things really start to get interesting. A sub 4 is a sub 4 minus 2 plus a sub 4 minus 1, which is a sub 2 plus a sub 3, which is equal to 2 plus 3, which is 5. A sub 5 is a sub 5 minus 2 plus a sub 5 minus 1, which is a sub 3 plus a sub 4, which is 3 plus 5, which is 8. So in other words, the Fibonacci sequence is defined as every term is equal to the sum of its two previous predecessors, its two immediate predecessors. And so that's what it means when it says a sub k is equal to a sub k minus 2 plus a sub k minus 1, where k is greater than or equal to 2 because we've already defined a sub 0 and a sub 1. Let's talk about factorial notation. Some very important sequences in mathematics involve terms that are defined with special types of products called factorials. So, if n is a positive integer, n factorial is defined as n factorial, that's the exclamation point, equals 1 times 2 times 3 times 4 all the way up to n minus 1 times n. A special case is 0 factorial, and we have simply defined 0 factorial to always equal 1. There's actually a reason for that. I'm going to say for right now, just accept it, and it will make your life way easier. So 0 factorial is 1. 1 factorial is 1. 2 factorial is 1 times 2, which is 2. 3 factorial is 1 times 2 times 3, which is 6. 4 factorial is 1 times 2 times 3 times 4, which is 24. And 5 factorial is 1 times 2 times 3 times 4 times 5, which is 120. So these things get very large very quickly. So the value of n does not have to be very large before n factorial becomes extremely large. For instance, 10 factorial is 3,628,800. So yes, factorials grow very, very fast. Factorials follow the same conventions for order of operations as do exponents. So if you were given 2n factorial, that's actually 2 and then in parentheses times n factorial, which is 1, 2 times 1 times 2 times 3 times 4 all the way to n. But if you're dealing with 2n in parentheses and then the factorial outside, that's different. That'll go from 1 times 2 times 3 times 4 all the way up to 2n. And so there's a big difference between 2n factorial without parentheses and 2n inside parentheses with a factorial on the outside. So just be aware of that. Example 5, writing the terms of a sequence involving factorials. So if I have a sub n is 2 to the n over n factorial, let's begin with n equals 0. So a sub 0 is 2 to the 0 divided by 0 factorial. Well, 2 to the 0 is 1. And 0 factorial is 1. So 1 over 1 is 1, which means the first or the 0th term is 1. A sub 1 is 2 to the 1 over 1 factorial, which is 2 over 1, which is 2. So the first term is 2. A sub 2 is 2 to the 2 over 2 factorial. That's 4 over 2, which is 2. So the second term is 2. A sub 3 is 2 to the 3rd power over 3 factorial, which is 8 over 6, which reduces to 4/3. So the third term is 4/3. A sub 4 is 2 to the 4th over 4 factorial, which is 16 over 24, and that reduces to 2/3. So the fourth term is 2/3. It's also possible to view sequences in your calculator. Set your graphing utility to sequence mode. Let me show you how to do that. So okay, here's our standard TI-84. Let me make sure everything's cleared out. Good. All right. So I want to be able to set this into sequence mode. So what I need to do is go to the mode key. So you hit the mode key, and what we do is we scroll down and we change it from function and we go all the way over to sequence. I hit sequence. Once you've done that, you can exit out of this. Now when you hit the y equals key, you're going to see something dramatically different. So this is a sequence, and the way that it works is you've got an n min, which is 1 in this case, and then the function, which we're going to define. So let's see if we can define this. Let's set n min equal to 0, just like they do there in the book. So that means that the number n is going to start at 0 instead of 1. And then what we need to do is we need to define our function. So 2 to the n divided by n factorial. Let's do that. 2 raised to the n power. I hit the variable key, and it's not going to give me an x. It's going to give me an n. And now I have to divide this by n factorial. So n, and then I need to get the factorial. I think that's under math, but I could be wrong. It's under probability. There we go. So you hit the math key, and you go to prob, which stands for probability. And there's the factorial. Sweet. So now I have 2 to the n divided by n factorial. And I think that's all I need to define here. Yes. So, okay, let's check this out. Let's go to table. Created a table of values. Let's go second. That was trace, I'm sorry, second table right there. There we go. So it started at 0. So 0, 1, 1, 2, 2, 2, 3. There's 4/3. There's 2/3, and it shows me a whole list of values. And so that is how you can define a sequence in your TI-84. Example 6, evaluating factorial expressions. Let's evaluate each of the following. Well, what if I have 8 factorial over 2 factorial, 6 factorial? Well, it turns out that I can take 8 factorial and expand it. 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8. And I can take 2 factorial and 6 factorial and expand both of those. 1 times 2, there's my 2 factorial. 1 times 2 times 3 times 4 times 5 times 6, there's my 6 factorial. But look at all the things I can cross away. 1, 2, 3, 4, 5, 6 can just cross away because they're all common factors between the numerator and denominator. So I'm just left with 7 times 8 over 2, which turns out to be 28. Okay, what if I have 2 factorial times 6 factorial over 3 factorial times 5 factorial? Well, 2 factorial, 1 times 2. 3 factorial, 1 times 2 times 3, so I can cross out the common factors of 1 and 2. 6 factorial, 1 times 2 times 3 times 4 times 5 times 6. 5 factorial, 1 times 2 times 3 times 4 times 5, so I can cross out all the factors of 1 through 5, and that leaves me with 6 over 3, which is 2. N factorial over n minus 1 factorial. Well, by definition, n factorial is 1 times 2 times 3, then an ellipsis, times n minus 1 times n. N minus 1 factorial starts at 1 times 2 times 3, then an ellipsis, and it stops at n minus 1. So we can cross out all the common factors, and that leaves us with n. So that's how you can evaluate factorial expressions. Summation notation. This is going to be used quite a bit in calculus. There's a convenient notation for the sum of the terms of a finite sequence, a sequence that terminates. It's called summation notation, or sigma notation, because it involves the use of the uppercase Greek letter sigma. Definition of summation notation. The sum of the first n terms of a sequence is represented by the following. Sigma, where I begins at 1 to n of a sub I, is equal to a sub 1 plus a sub 2 plus a sub 3 plus a sub 4, all the way up to a sub n, where I is called the index of summation, n is called the upper limit of summation, and 1 is called the lower limit of summation. Make sure this gets into your notebook. Let's show you an example of how this works, and it's going to make a lot more sense. So, okay, let's begin with the following. The sum, where I begins at 1 to 5 of 3i. This is how it works. The sum of where I begins at 1 to 5 of 3i is equal to 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 times 4 plus 3 times 5. The I is the index, so it changes each time. It begins at the lower index, 1, and it will end at the upper index of 5, and it will become everything in between. So now you just evaluate. Factor out a common factor of 3, Add up 1 through 5, which is 15. 3 times 15 is 45. So the sum turns out to be 45. Here the index begins at 3 and then it ends at 6. The index is now k. It really doesn't matter what you use as an index. I, k, whatever. So 1 plus k squared. So again, the index always begins at the lower part of the sum and ends at the upper part of the sum. So this is 1 plus 3 squared, plus 1 plus 4 squared, plus 1 plus 5 squared, plus 1 plus 6 squared. 10 plus 17 plus 26 plus 37 is 90. So this sum becomes 90. The sum, where I begins at 0 to 8 of 1 over I factorial. Remember, the index starts at the lower sum and ends at the upper sum. So this is 1 over 0 factorial, plus 1 over 1 factorial, plus 1 over 2 factorial, 1 over 3 factorial, 1 over 4 factorial, all the way up to 1 over 8 factorial. And so we get the following expressions. 1 plus 1 plus 1 half plus 1 sixth plus 1 24th plus 1 over 120, all the way up to 1 over 40,320, which is approximately 2.71828. For this summation, note that the sum is very close to the irrational number e, which is approximated as 2.71828. It can be shown that as more terms of the sequence whose nth term is 1 over n factorial are added, the sum even gets closer to e. Now here's some important properties of sums. It turns out that if you're adding, where the lower index starts at 1 to n, if you're just adding a constant, a number, and nothing else, the index isn't part of the expression, then the result will always be the constant times n. If you're adding up, I starts at 1 to n of a constant times a sub I, then the constant, as long as you're multiplying it by a sub I, can be factored out of the sigma. In other words, it can be factored to the front. That's always true. If you're adding from the lower sum to the upper sum of a sub I plus b sub I, you are allowed to separate this into two different sigma notations. The sum where I starts at 1 to n of a sub I, plus the sum where I starts at 1 to n of b sub I. Likewise, if you're adding up the difference, I starts at 1 to n of a sub I minus b sub I, then you are allowed to separate this into two different sigma notations. The sum where I starts at 1 to n of a sub I, minus the sum where I starts at 1 to n of b sub I. Let's talk about series. Many applications involve the sum of the terms of a finite or infinite sequence. Such a sum is called a series. Consider the infinite sequence, a sub 1, a sub 2, a sub 3, all the way up to a sub I, and then it just keeps going. The sum of the first n terms of the sequence is called a finite series, or the nth partial sum of the sequence, and is denoted by the following. A sub 1 plus a sub 2 plus a sub 3, all the way up to a sub n, is equal to sigma, where I begins at 1, to n of a sub I. The sum of all the terms of the infinite sequence is called an infinite series, and is denoted by the following. A sub 1 plus a sub 2 plus a sub 3, all the way up to a sub I, but then keep going, is equal to sigma, I starts at 1, to infinity of a sub I. So let's make an example, or let's take an example to make this a little bit more clear. For the series where I starts at 1, but actually goes infinite, of 3 over 10 to the I, find the third partial sum, and then in part B, let's find the actual sum. So to find the third partial sum, instead of going to infinity, we're going to end at 3. So we're going to make this finite. So the sum where I starts at 1 to 3 of 3 over 10 to the I is 3 over 10 to the 1 plus 3 over 10 to the 2 plus 3 over 10 to the 3, which becomes 0.3 plus 0.03 plus 0.003, and that turns out to be 0.333. So that's the third partial sum. But now part B says, what is the sum? That's your definite article. Well, that means the sum means we want to go all the way to infinity. Well, what we're going to do here is really just look at the pattern. And from the pattern, we're going to infer what it has to be. So if I go all the way out, for example, to the fifth sum, I notice I get 5 3s. And so if the 3s go infinite, which they will, what we're really getting is 1/3. And what that means is that the sum, where I starts at 1 to infinity, of 3 over 10 to the I, is the fraction 1/3. So that is the sum, even though it's infinite. All right, applications. Let's look at a compound interest problem. A deposit of $5,000 is made in an account that earns 3% interest compounded quarterly. That means 4 times a year. The balance in the account after n quarters is given by the following. So A sub n is the balance after n quarters. 5,000 is the deposit times 1 plus the rate divided by compounded quarterly. So this is 4, all to the nth power, where n equals 0, 1, 2, and so on and so forth. Write the first 3 terms of the sequence. Then find the balance in the account after 10 years by computing the 40th term of the sequence. So, okay, the first 3 terms are following. Just replace the powers with the appropriate numbers and then use your calculator. 5,000 at the beginning, then $5,037.50, then $5,075.28. And those are the first 3 terms. Now, after 10 years, remember it's being compounded 4 times a year, and that's why we have to put in 40. 4 times a year for 10 years means it's compounded 40 times. So this is a calculator problem. We take 5,000 times 1 plus 0.03 divided by 4, all raised to the 40th, not the 5,000, just what's inside here. And it turns out that what we're going to get is $6,741.74. For the years 1980 through 2007, the resident population of the United States can be approximated by the following model. So here's a polynomial which models this problem, a population problem, where A sub n is the population in millions, and n represents the year, with n equals 0 corresponding to 1980. Find the last 5 terms of this finite sequence, which represent the U.S. population for the years 2003 through 2007. So, okay. Remember, A sub 0 corresponds to 1980, and we're talking about a span of 27 years. So we could actually work this problem backwards by starting at A sub 27, and then plug 27 into this polynomial. So remember, this is in millions. So in the year 2007, 303.4 million. In the year 2006, 300 million. 2005, 296.7 million. 2004, 293.5 million. And then 2003, 290.2 million. And there you go. That is the lesson. God bless you wherever you are today.